Bueno, buenas tardes a todos. Gracias por venir al seminario. El día de hoy tenemos el gusto de contar con la presencia de Damien, quien viene de la Escuela Superior de Tecnología Superior de la Universidad de Quebec. Él es jefe del Departamento de Ingeniería y Construcción allá y entre las líneas de investigación, bueno, tiene mucha experiencia tanto en laboratorios como en consultoría y trabajando para diferentes dependencias de gobierno. Entre las líneas de investigación principales que cultiva actualmente está la hidrodinámica y transporte de sedimento tanto en ríos, estuarios como en costas, así como el estudio del transporte de sedimento asociado a las ondas o al oleaje generado por embarcaciones, que es el título de la presentación de hoy. Gracias, por
Thank you, Alec and Christian, for inviting me, giving that quite original talk because I'm here with coastal engineers. That topic deals with waves, but in a river context. So because in river we can have specific wave, which is a boat wave. So here is some illustration of the issue. So we have Montreal here, we have the ocean there, and because of commercial world trade, there is bigger and bigger ships passing at higher and higher speed, making larger and larger waves. And sometimes this wave can erode, similar to wind wave. But we will see that how both waves are specific in what they differ from wind wave. So first, just to, I would like to thank some funding agency that are more or less interested in coastal engineering for environmental purpose, for economical development, for green growth, blue growth, and so. I think it's everywhere in any country it's the same. Would like to introduce my research share. So here at ETS, we have 4 PhD students working on numerical model, and we also have collaboration with my previous lab at INRS, where we mostly develop experimental work in wave flume. So the specificity of wave flume in Canada, in Quebec, is we have access to a very large wave flume. This is 5 meter width, 100 meter long, to generate a wave up to 2 meters height. And here is some experiment with real vegetations with the target to dam waves in order to reduce erosional properties. And we also develop small scale for physical process with wave interaction with structures or with sediment transport processes. So here we can see PIV measurements, for instance. We also are one of the first teams to develop coupling of technology. For instance, here we mixed medical device like a CT scanner that you can use for your medical, with also echo Doppler imaging to measure a physical process associated with sediment transport. Here you can see a suspended load under oscillatory flows. Here, if we digitalize a picture, we can count, make some Lagrange measure sediment transport. And here is some illustration of what we can do with coupling technology. Here is an example on scar erosion. So you have a pile, and the pile is on sea floor, and with a wave or current that can erode, it accelerates the flow and remove sediment. So after some times, the scar hole can be very big and very large. So the stability of the structures can be compromised. So of course, we have observation in high resolution, non-intrusive manner for the topology for topometry. We also have PIV measurement for the flow velocimetry, and we develop numerical model to extrapolate the observation in a real world. Okay. So, for instance, for seawall, maybe there is a relation with the glowing. Okay, we worked for the Ministry of Transport on tow erosion at seawall. So in particular, we get an access with PIV to the flow field near the seawall. In particular, we can see that the vorticity field can contract, but also expand depending on the wave phase. Okay, and that oscillation irrevocably and in a hysteretic manner will little by little generate a scar hole like this. So the main process that we study with wave interaction to seawall inducing a scar hole is the flow deflection, generating a vertical impinging jet that is removed and generated dune like this. So we did that and we calibrate a numerical model to capture the morphodynamics in the near in the vicinity close to the structures. So here you can see the dune here and the scar hole there, starting from a very straight and mild pitch profile. Also in our team, we did some numerical model, very large scale. This is a Rio de la Plata, close to Uruguay. Here we measure, we compute based on measurements, okay? Salinity, wave, and velocity. In particular, to measure, to have, to see or to capture the process siltation in the Hebo basin. So from numerical model, we can see or capture the two patterns of flow circulation inside the Hebo, which is responsible for large siltations. So the siltation in Hebo is bad point because you need to dredge the basin in order to guarantee the nautical depth, so the boat can pass with no problem. So here, now coming back to the topic of my talk about the boat passage, here is a view of one traffic scenario, so one large vessel passing from the left to the right. And after that, we can see the ship waves, which looks quite gentle until it reaches the bank of the island, but it overflows and overtop the bank, and then you will see the reflections. Here you can see some partial erosions, and here you can see the reflection of the waves. So coming and here, so we in that region, we consider that most of the bank retreat, almost 2 meters per year, is associated to ship waves. So that's why we started to study that in a coastal engineer manner. And we will see how different is the waves. Okay, so yeah. So, as you can see here, it's a International Association of Navigation. There is a lot of work. It's a long-standing problem to evaluate how boat waves can be responsible for bank erosion. So, and from the lesson learned from past study is boat waves depend on shape of the boat, depend also on the ship, and sometimes with frequency of traffic, we can have interference of wave pattern. So it is that association identify different effects of boat passage. So in particular, the primary waves, the secondary wave, and the impact to the bank in terms of pore water pressure in the bank, also the drying, wetting mechanism, also the wave breaking, the environmental effect with sediment transport is a turbidity increase that will have an impact on the biota. Can, for instance, reduce the photosynthesis. It creates anaerobic conditions. So it's also scarring because sediment can be very localized at the toe of a dune or something like that. So, and this picture shows you how complex is a process of destabilization of a bank by a boat wave. So, of course, it is well known, and we still don't know how to make the balance about responsibility. What is natural process of erosion? What is anthropogenic nature? And the question is more and more important because of the development of trade, world trade between countries. For instance, there is a commercial agreement between Canada and Europe. There is will be another one with Mercosur with South America. So the traffic will increase. As you can see, it's just a small sequence, but you can see that with that statistics, we can estimate that we have 6 million containers a year. Every year, there is 6 million containers more than so. And of course, the ships change. As you can see here, some sequence relating the size of the ship. So this is some more than 15 years ago. We have this small capacity container. Here is the number of container. This is here the size, 1 to up to 400 meters. So with that statistic, we can say that every 16 years, the length of the ship, commercial ship, double. Or in a short, or you can also consider that the ship is growing 5 meters a year. And the capacity is around 200 containers every year. So the question now is how, from the lesson learned from boat on small vessel, how can we predict the impact for the future vessels having larger size, moving faster and faster, and potentially generating higher and higher waves. So this is one slide, only theory, what we know about ship. We know that the ship wave is mostly based on Kelvin waves, on Lord Kelvin, who demonstrate with a linear theory that a moving pressure will generate two kinds of waves. One type is the transversal waves, that is transversal waves, and the other one is the diverging waves. Okay, and the interference between these two types of wave create a caustic line or cusp line here, having geometrical properties very strict, which with inclination equal to 90 degrees, more or less. We know also that the wavelength or the distance between two crests of transverse wave is related to the length of the boat. Okay. Of course, it is only linear theory, but it works quite well with the majority of waves. This do not predict the height of the waves. Okay, and you will see that's another issue. An interesting thing is that the theory is only based on the assumption that we have a pressure moving. So it means that this kind of theory can exactly explain other natural waves, like the duck's wave. Okay, duck's wave is, it's just a small animal making some pressure and moving. So it applies a pressure, and we have the same theory. The same theory applies to explain that. We have the same type of wave, diverging, transversal, interference, cusp line. Of course, the problem is much more complex in natural conditions because boat has exactly 6 degrees of freedom. So with the position of the boat, with the angle, that can affect the wave pattern. So linear theory provides that kind of pictures. And of course, now we can deal with non-linearity. So that problem, we have different non-linearities that deviate from the Kelvin Lord theory. One deviation is the velocity of the boat. Here is what we know about the velocity effect on the wave pattern, the moving ship. The first is the angle of the cusp line from subsonic, I would call subcritical speed, meaning that the Froude number based on the length of the boat is smaller than the speed velocity, critical speed, or in the very high speed or supercritical or supersonic speed with a decrease in the cusp line angle. So you can see here the general results here, showing that if the boat moves faster and faster, or if you use a big zodiac, or you will see the angle is like that. Another phenomenon with speed is also the speed of the boat comparing to the upstream wave, the bow waves. So if the boat speed is higher than the bow wave, it will surf on the bow waves, and we can have some kind of tendency to lift. Now that is typically some nonlinear effect due to the boat speed. You can also have this hesitation to lift, and that will induce another frequency. Another nonlinearity is interaction of waves with current. That's very common for a coastal engineer, and we know how complex are the development of nonlinearity. So, for instance, here is ambient current transversal to the sailing line, and you will see the wave pattern tend to deviate. Its deviation is stronger with strong lateral ambient currents, and that changed completely the wave pattern. So the frequency, the direction, of course, and wavelengths. We will see also some Doppler effect, in fact, due to that interaction of wave and current. Here you can see here a superposition. If we increase the frequency of navigation, if you have from 1 boat a year to 10 boats every hours, okay, then the wave pattern generated by the first boat can still survive when the second boat passes. In that case, you can have a superposition of waves that can be constructive. Here you have an increase of wave height due to the first wave pattern. And of course, you can also take the benefit if you use this kind of arrangement. So in that case here, the oil consumption of the second boat is smaller than the first. Maybe why? That's why you can see ducks family swimming together, okay? Because the small ducks want to save energy. Okay? And the mother duck is first on that peloton. Okay. Here is also an explanation of ambient current with wave. Okay. So similar. Here is the case with navigation along the current, and this is a navigation with adverse current. So you will see that the problem is completely different. In particular here, okay, where here you have that layer of fluid moving with the boat, and that one moving in the opposite direction. So it means some kind of velocity profile like this. So we know that that point is unstable. So here we will generate some turbulence here. In that case here, we still have some deflection, some convex point, some inflection points here, but the turbulence will be smaller than the previous case. And of course, in terms of oil consumptions, that is more expensive here than that. So, but conceptually, we can still think that boat wave can be studied as any waves as coastal engineer, meaning that you have the source of wave, the passing boat, which shear the water surface, generates waves, and then the wave propagates and will transform along its pathway, transform with the same process, I guess, with a shoaling, with a braking, having run up also. So I would say that the wave will erode the shorelines in a similar manner than any kind of waves, in fact. But we think that, of course, the sources would be different due to the non-linearity I mentioned, the boat speed, the trajectory of navigations, the direction with ambient current. But at the end, we believe that we still have the same process for erosion. Okay, so there is a critical speed. If the speed flow is larger than critical value, it will erode, and erosion mean bed load and suspension and distribution like this. Oh. To test that, we did 2 days measurement in field. So this is field team. I'm here. So for that, we use 5 stations. Okay, to measure wave height in 5 points in order to determine the direction of the waves. And in that station, we had measurement on water height, turbidity OBS, velocity, and also turbidity and water quality. So unfortunately, during that survey, we had a strong wind. But it was interesting to see the difference between boat wave and wind wave in terms of direction. Okay, so here in particular, we have wind speed from that direction and a boat passing like this. So in that case, we can clearly see the nature of wave with the signature in their direction. And we can also see the interaction between 2 waves propagating in different directions. We also repeat another survey, another site, where happily in that case we didn't have wind wave or few wind. And for that, we try to measure the velocity, the sailing speed of the boat using this kind of technology. It's used by policemen along the highway. So just shooting with laser gun to measure by Doppler effect the velocity of the vehicle. We also develop some small drone to make measurement in very shallow water. In fact, a windsurf planche is also windsurf board can do that. But here we have a high velocity, so it can be dangerous to use a windsurf board. And here is the deployment site here and here, which is a part of the natural island, which is very precious for Quebecers, as it is a biological reserve, natural, and this part is owned by the Nature Conservation Canada. There is a lot of interest for fish or special species with fish and with bird. And as you can see, that is some accumulation of erosion due to boat passage. Okay, here, this width is around 600 meters. So it's very narrow if compared to the boat width. Okay, the boat width is around 110, 50-meter width. and the width, the channel width is around 10 times the boat width. So it is considered as being very narrow here. So during that, we put some ADCP here, some wave height measurements, turbidity, and we shoot laser gun to measure the velocity of the boat. And it was under low wind conditions, and we measure this kind of wave pattern. So this is a mean river line or sea line, okay? And here, any oscillation like this are three boat episodes. One is a container ship, another one is recreational, small, and the last one is a liquid ship, a ship which transports liquid, can be oil, for instance. This is a typical size here. This is the draft, and this is the speed. So we mostly focus on this case and this case as being two opposite, two asymptotical case of boat traffic in that zone. So in the first case with container ships, if we zoom out the wave height signature, we will see here a very low frequency followed by high frequency wave signal. We try to decompose, analyze that wave signature, making wavelet transform to make some time frequency analysis. So that analysis show that we have a high speed, high frequency that tend to decrease over the time. So it means that we have a high frequency contained starting around here, and low frequency is very local. Remember that is here also the primary wave, and from that we have a secondary waves. So the one interpretation of that analysis is primary wave have short period, short duration. It doesn't survive a lot, but it's low frequency. And high frequency have a longer duration. So it's quite strange. This is a recreational boat. So here we have high frequency everywhere. We cannot see low frequency. So it was difficult. Maybe we have to have more study. One reason to consider the opposite commercial large ship with recreational small ship is we can cover a huge range in velocity Froude number, and we can also cover the different distance to the beach, because behavior of pilots is very different from a commercial ship and the recreational. So we wanted through that case, we wanted to see if there is some recommendation for pilot to use better the ship in a given place where the river narrows. So, and finally, type of our study in my group, we finish with numerical model. So this is a Telemac model. So which is we know well that generation of model. This is Montreal is here. So if you come, Montreal, welcome. Here is a target of study. Here you have a narrow river. Here in blue line you have the talweg of the river, meaning the deepest zone. And here is some first calibration with natural traffic. So here we calibrate with discharge and water level. And then we start using the first category of model, I mean the moving pressure point. So here we activate, or we activate the new development, which says Dux wave model to mimic ship waves. So here we have two illustration of the method. One is Eulerian, the other is Lagrangian, but in average we have the same wave pattern here. And we also change the boat speed in order to test and validate qualitatively the angle of cusp line of the ship. So here it's a high-speed vessel, so the angle tends to decrease compared to that here. Here the ratio is around 10, so it means one boat width is around 10 narrow. And we also test the draft of the vessel here. Means that if the ship is empty or not. Okay. And finally, here is the highest category of model, which is not operational anymore, which is, I would say that it's the best CFD that we can do nowadays on that kind of topics. It is called 3D, VOF, volume of fluid, and DNS here. So that simulation was done by my associate CAD here. And as you can see here, we can have wave breaking, some air bubble entrainment, and we can also capture the primary and the secondary. So the idea now is to improve the first Dux wave model based on this high-level model in order to have to make prediction for future vessels in size and speed. So just some conclusions. Of course, erosion is a natural hazard, which can be amplified by human activities. And among that human activities are ships. Ship is necessary, but the tendency of their evolution will maybe induce new problems in terms of conflict of use the water plan. Thank you for your attention. Just to remind you that we organized in Quebec City a conference on estuaries and coast with Alec here. Thank you. Yes,
Were you able to model the erosion with the telemech?
not yet, not yet. For the moment, we spend most of our efforts on the hydrodynamics. Erosion is a consequence of hydrodynamics. Of course, with erosion, it will modify the geometry, so the hydrodynamics. So first, as a first step, we want to focus on the hydrodynamics. And in this case, it was quite difficult. But now, and after that, we have erosion. But erosion is will add another degree of complexity, because here, as I explained here, the natural process, the physical, the very is difficult for hydraulic engineering. I mean that for river banks, having large slope made with cohesive sediment, there is some pore water pressure effect within the soil that is difficult to handle. I think that with sand, I would say that maybe it's more easy because sand beach has high porosity, so the pore pressure cannot accumulate too much. But no, we didn't start erosion yet.
And so, how would you think the erosion will be in an area like a channel where there's a port?
Mm-hmm.
So the ships are coming in,
yeah,
but then the ships are going out, right? So sometimes you have waves this side and sometimes waves this side.
Yeah.
Do you have any thoughts of what will dominate, if the transport to this side or the transport to this side?
In the case of Sisal, maybe you think about this Sisal port.
I'm thinking of another.
Yeah,
port.
Alex showed me a big sand pit at the entrance of airport. So it means that there is a sediment source localized here. So maybe there is more sediment coming in than coming out. And because if we consider the airport as being quiet climate of waves, so the motion diffuse from high agitation to low agitation, so the flux is in. So.
Yeah, it's, I mean, it's similar or probably in the line of Christian's question. How does the current affect the wave propagation? Like you have the wave current interaction, and in some places when it gets narrower, the current gets higher.
Yeah.
So, and also if you have seen, you showed us places where you have seen like the retreat of the line, no? The shoreline.
Yeah.
If there are places where you have seen like accretion.
Yes. 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 So because we didn't study erosion, we didn't study accretion, but that's right. That in this context we didn't study that. But okay, with the interaction with current is quite. With that picture, it shows you that, and only Doppler equation will explain you main part of the problem. Here in that case, you will see wavelengths shorten. Okay, and that is a wavelength has tend to increase, and so that is the main mechanism of that. Also, I would say in case of non-aligned wave direction and velocity, you have this kind of convection of waves that tend to distort the wave pattern. So the consequence is here you have wave moving like this, but ambient current like that. So you shorten the wavelength, but in that case you have increase in wavelength. So this creates some asymmetry that we don't have in a linear theory. So on the right side you have a shortened wavelength, on the left side you have longer. So yeah.
Just out of curiosity, if there's like a seasonal variation on the boat traffic and also in the current, no, like
yes,
rain season,
yes,
they match.
Yeah, there is seasonal effect, but not at the sense as you think. Okay, the seasonal effect is ice and winter. During the winter, most of the St. Lawrence River close to Montreal has high sheet, so there is very few traffic. So no traffic during the winter. And summer there is a high traffic. Another seasonal effect is the ice melt of the Great Lake, because St. Lawrence River is supplied by the Great Lakes, the 5 Great Lakes in North America. So in that case, we have a discharge like this. In this portion, we don't have tide. I didn't mention that. It's right. In other places, there is a tide along St. Lawrence. In particular, in Quebec, we have a 5-meter tidal range. So, yeah. And now, yeah.
Thank you. You did mention that you sort of have a fingerprint of this both waves compared to wind waves.
Mm-hmm.
Is there some evidence that they are more or less destructive than wind waves? Have they a characteristic frequency different than wind waves? They're richer in terms of frequency or something?
Yeah, I think we can have. Thank you for this. I think we can see on that. Yeah. So, in the site, the main observation was with direction and amplitude. We didn't see clearly a strong difference in frequency. I guess because the point where we measure wave is detached from the origin of the wave. So in that case, when the wave detaches from its source, it becomes a wave. No more boat wave or no more duck's wave. It becomes a wave like any other. So for that, he adopts the dispersion relationship. So it's like losing memory of the boat. So we didn't see large, big difference in the frequency, only temporarily. because both wave is very localized in time. It's not a continuous. Here the sequence is it's okay, almost 10 minutes maximum. Okay, so with a different the frequency content looks similar to wind wave, but the duration of the wave train is quite localized in time. And direction depend on the navigation trajectories.
Thank you.
Hmm?
So do you have like evidence of this erosion from both waves? Here.
Oh.
Sediment.
It's quite a dream for sedimentologists to measure that. It's very difficult to measure erosion, except in some situation. The growing is one of it, because it's something who looks like diffuse in time. So it's, and you have to be to spend a lot of time at a given position waiting for erosion to make the measurements. It's very brutal. It's very difficult to measure exactly the erosion. So we didn't have that episode in today's field measurement.
What I mean is, based on what you present, the boats are bigger.
Yeah.
Maybe that means that it will be a time that maybe boats in these kind of places, like small reef, like in rivers,
Yeah.
boats can really mean a hazard for the erosion, and maybe they cannot be bigger than one size.
Yeah.
Just to not make it more harmful to the alien. I don't know.
Yeah, I think you made the same mistake as me. My mistake was to believe that big wave, big boat generate big wave. But it's not always the case. Okay, because yeah, it's not a question of size of the boat. It's question of the foot number. Here, the foot number decide here. So if in particular the original Froude number, Sir Williams Froude was a naval architect in UK. So he established Froude number based on ship length. And then we apply in river engineering for making transition between the fluvial and the torrential flow regime. So if you have a small ship, then the critical speed limit is lower. So the contrast between the navigation speed to the velocity, to the critical velocity, is larger for small boat. So for small boat, we have a larger Froude number compared to the large boat. In that case, small boats are more like this, surfing on its self-generated bow wave, and large vessels are like that. So, and we don't have the same. My mistake was to think that big boat make big wave. It's not the case.
Just have you thought of maybe using satellite images from some years ago and try to correlate that with the increase in traffic, in boat traffic? Maybe you see like a higher rate of shoreline retreat correlated with the increase of boat traffic. I don't know.
I think it's we didn't, but it's good idea. In particular, here, in fact, okay, here I think. No. In fact, we did not use satellite imaging, but we had aerial pictures. So it's just a plane and took pictures. But the guy did that in the past. Here. So is a times lapse. It's small character. Sorry, it's 2006. 2014, 2017. So from this kind of aerial picture, I think maybe it's a stereoscopic, but pictures. Then you can have this kind of digitalization, and that's why we can compute the bank retreat. The problem with that method is it's difficult to measure acceleration of bank retreat. Okay, but if we continue doing that, I think, and if we make the correlation with traffic, maybe we can draw some tendency. But it suggests that we can compare anything. Okay. And if you consider that the site change, so some nonlinear effect cannot be. Thank you.
Just a comment on both sizes.
Yeah.
I mean, they just cannot grow and grow because actually the big 20,000 BTUs, there's only few ports that can accept those, right? So just one. Actually, they're thinking of forgetting about those big ones. There's not that many ports.
It's a big boat, yeah.
There's not many ports that can accept those. So.
Yes, but yeah. It depends on country, of course. Here in France, because I didn't mention that I'm French. We have many ports in Antilles. I guess in Guadeloupe, Martinique, and all of this administration want to have Panamax cargoes because of the proximity to the Panama Channel. And there is another, I think it's a Chinese new channel. So they want to increase the boat size for that. I think Progresso is only gas terminal or oil terminal for boat. No, Progresso there is no terminal. There is.
Yes,
It's oil.
No,
gas terminal. So for that, of course, the size of the ship is interesting.
Yeah. There's only 10 meters.
Yeah. Yeah. Of course. Yeah. Yes. Sure. It depends on the water depth. But in case of sport, deepen the navigation channel with dredging. So that's another question. Yeah.
Just a quick question. How much can change the wave spectra for the same boats depending on the velocity? Because at the end the waves can generate a clipping
Yeah.
or erosive condition, and if you're able to find like the right velocity, because most of the time one thing, if it goes faster, it will create a larger wave and will be worse. But maybe because of the frequencies,
Yeah.
will be not as it's not as linear as one would think.
Yeah, thank you. I didn't think about that, but you're right. We can suspect some variation of wave spectrum with nonlinear stuff of navigation scenario. Okay. I would say that maybe this picture can help. I didn't. Okay. Here, this picture can help to provide some if the boat speed is faster, it will modulate the wavelength, so the frequency. So it will maybe shift the peak frequency of the spectrum in a manner. I guess faster is higher speed, frequency. But I need to to check. And yeah, yes, it is not taken into account in this kind of study, probably because it's difficult to control the cruising speed of the boat. We are just spectators, and we just measure the ambient traffic. But to investigate that, we need to yeah, sure. Yeah. That is another aspect of numerical models which can extrapolate. Thank you.